We welcome Dr. Manavendra De. He is already with us. Namaskar, sir. Before we begin the session, which will be conducted by Dr. De, I'll just briefly introduce him to all of you. So, Dr. De is a principal scientist at the Systems Engineering Division at CSIR-Nal, and he's also an assistant professor at the Academy of Scientific and Innovative Research. Dr. De holds BE Mechanical Engineering from South Gujarat University, and he has done his MTech with specialization in turbo machines from SVNIT Surat. He has done PG Diploma in Intellectual Property Rights from IGNOU and WIPO, and PhD degree in Applied Mechanics, Computational Fluid Dynamics from IIT Madras. He joined the CSIR-NAL, Bangalore, in 2006 as Junior Scientist in Wind Energy Division. At present, he is serving as Principal Scientist in Systems Engineering Division. He holds an honorary assistant professorship in Academy of Scientific and Innovative Research, which is ACSIR, New Delhi. His research areas include applied CFD, system engineering, wind turbines, rotor aerodynamics, AS9100 certification, and IP rights. Okay, Dr. De serves as a subject expert in international and national committees. He has over 30 research papers in national and international SCI journals and conferences. He has been granted 2 Indian patents in the field of renewable energy, wind turbines, and flapping wing aerial platform. He is involved in guiding students for the final year project works, internships, and serves as a thesis examiner for PhD and MTech students. He has also guided a student from FOSSEE internship, and his work will be presented as a case study demonstration just after Dr. De's talk today. So it was a brief, background of Dr. De. And over to you, sir. You can start the session. We are really humbled and we are thankful to you that you have come here sparing your time from a very busy schedule. And we'll be happy to start the session with you.
Okay, ma'am. Thank you. So, yeah, good afternoon, everybody. So, I would just like to tell a small story from history, and then try to say why I correlate my talk with that. So, all of us know that there's a small community called the Parsis who came from Iran to India somewhere during the 8th century. So when this convoy came from there, they landed at Sanjan port, which is part of Gujarat, my home, my birth state. And when they came and got down at the port of Sanjan, they wanted to take permission from the ruler, the king who was ruling that region during that period. And as a response to their request, the king had sent a pot full of milk. And in response to that, what the Parsi community did was they dissolved sugar in that milk in a pot without spilling any of the milk which was there in the pot, and then sent it back to the king. And then when the king tasted the milk, he accepted the request of the community to stay in that region. Now, this is as far as the history goes. So, in today's context, if I say my presentation, rather than being a milk which I would try to pour into all your minds, I would like it to be like a sugar which gets dissolved into the already existing milk, which is in the form of the presentations which the previous speakers had given in the last 3 days, and if even today morning. Uh, we had a very interesting talk, and at the same time, the demonstrations that have been already given. So your mind is full of that milk in the form of all this information. So this presentation today will be more like a sugar, which will try to slightly add to the value of that milk, which is already there with you. Our discussion today will be on the challenges that the renewable energy harvesting community is facing and what can we expect from the CFD community. Of course, today, rather than carrying my portfolio as a scientist or a PhD holder or maybe somebody who is in a government firm, I am standing or I'm presenting my thoughts in front of this august audience, which is consisting of professors, postdocs, PhD students, undergraduates, postgraduates, and enthusiasts in CFD community. And as a common man, I'm just trying to put forth before you the issue which I am facing at the grassroots level, which is the energy. The energy is one of the problems that we are facing today in various walks of our life. And then I have something like a solution to solve that problem, which is in the form of harvesting the renewable energy. But then, in that context, how this community can help me, the CFD community that can help me, that will be what will be the flow of the discussion today. So, we will go in the following manner. We'll just quickly go through the overview of Council of Scientific and Industrial Research, CSIR, and then quickly go through NAL, and then have a bird's eye view of the renewable energy harvesting efforts that were put in NAL, and then a glimpse of some of the works that we did using CFD to help in our renewable energy programs at CSR and NAL. And then finally, we come to the last portion wherein we will try to discuss some challenges and what is it that is expected from the CFD community, the FOSSEE community. And so FOSSEE is an umbrella under which there are a lot of open source software communities that are existing. So right now we are talking from the point of view of CFD, but as you would see, many of the problems will need help from the other disciplines also. So how does the community help us in solving or at least getting some hint on handling those challenges, and then end the talk with few thoughts of mine. So coming to the first point, basically, Council of Scientific and Industrial Research is a pan-India chain of research institutes which work on various disciplines of science. So we have labs from which work on chemical science. We have labs which work on biological science, physical science, earth science. NAL specifically, we are into the engineering sciences. So you can see all across India, we have our presence. Coming to NAL, we are at Bangalore, and our primary focus is on aerospace research. And as you can see, it is a bouquet of various disciplines that we have in NAL. You can see CFD is one of the areas. Apart from that, we have other disciplines also, composite structures, we have material science, and then electronics, structures, experimentations. So all these disciplines, there are small divisions or labs in NAL, and cohesively they all work towards the primary focus of aerospace research. Now, when we do such research, it is very natural that we come out with some of the spin-offs which are applicable to the other domains also. So, in that context, our expertise in turbo machines, which is very core expertise niche area required for the aerospace research, the spin-off of the turbo machines has led to technologies in the renewable energy domain. So that's where today we will have a glimpse of those works that we did, and then in that how and where the CFD community and the open forum community present over here can make significant contributions in the coming future. So basically, NL works in a consortium kind of a mode, and we always welcome networking with academia, with the public sector undertaking like HAL, the line ministries or the research labs under those line ministries like defense or department of space, And also we work with the regulatory bodies because it's aerospace. You cannot leave the regulations and the guidelines, the regulatory norms which need to be followed for the aircraft design. So we also work with the regulatory bodies, and also there will be glimpses of international collaboration, even in renewable energy. Towards the end of the presentation, where we have done some work with under the Danida program. So we'll have a look at it in a couple of slides from now. So as I was mentioning, we have core technologies and strengths have been developed in NAL in various verticals of research. And what we will be today talking a little bit more is about the turbo machinery, and then about the wind turbines, and of course the surveying and measurement aspects of wind turbine and solar energy, and then see how the problems that are existing can be addressed by this august audience today. So coming to the renewable energy harvesting efforts, we have again three verticals over here: geothermal energy, solar energy, and wind energy. Now, please keep in mind the things that I told in the previous slides. We are talking about the spin-offs from the turbo machines. So even here, you will see that somewhere the flare of turbo machine is existing in the efforts to harness the renewable energy. So coming to the geothermal energy, this is typically the overall architecture of the plant, where you see that our core expertise in turbo machinery has been employed in designing the turbine. Of course, when you talk about harvesting energy, I cannot just stop at only designing a component. So NAL did some pioneering work in this development of this entire system, starting with a pilot project using the industrial waste heat, and followed by geothermal energy, harvesting geothermal energy, and then subsequently solar energy also. So basically, this entire cycle is an organic Rankine cycle based power plant. So we are very well aware about the Rankine cycle, which is the thermodynamic cycle which governs the operation of a steam power plant. So in this case, instead of water as the fluid, organic compounds have been used as the working fluid. And the reason being that to change the phase of an organic compound, you need relatively less temperature gradients. And that was the thought process behind realizing an organic Rankine cycle. So this is something which we would have learned in our school days also, like what is geothermal energy and how does it get visible to us, what is the mechanism, how the magmatic intrusions they form the source of the thermal energy, and then how it percolates through the impermeable rocks, and then gradually gets visible in the form of either geothermal well or hot springs over here. And there are a lot of areas in across the world where you can see the existence of such locations. And primarily, one should be aware that these areas are located in the tectonic boundaries. So you will find more of these geothermal sites in areas like, for example, in India, if we say it will be more in the Himalayan belt, or somewhere here in the Western Ghats where you have mountains and there is a constant tectonic movement that is sometimes visible in these areas. So this is the overall provinces in India where we can uh, see the presence of geothermal energy. Around 10.6 gigawatt is the estimated potential of geothermal energy in India. And there are various sites that have been identified by Ministry of New and Renewable Energy. You can see over here in various parts of India where the existence and the possibilities of setting up the geothermal power plants are possible. So in this context, what NAL did was using the turbo machine, the entire setup was first demonstrated at NAL. This I'm talking of the time something around 1985, when many of us in the audience might not have even born. So during that period, this work was taken, and then an actual plant was installed at Manikaran in Himachal Pradesh. This was a 5 kilowatt geothermal power plant, which used the Freon 113 as an organic fluid for the Rankine cycle. Now, having done that, the next approach was to again translate the same technology for solar energy harvesting. Now, when we say about solar energy harvesting, primarily what comes to our mind is the photovoltaic cell. But there is also another approach of harvesting the thermal gradient of the solar power in various forms. So one of these form is the solar pond. So in this context, again, NAL tried to see how, again, the know-how which was developed by demonstrating the organic Rankine cycle uh, based geothermal power plant, how can we again use a different form of heat on the same cycle? So in that context, this was another program which NAL took during those days on the solar pond based energy generation. So again, here basically it is an artificial pond, and there are three layers as you can see over here: the upper convective layer, and the non-convective layer, and the lower convective layer, which is mainly from where the thermal fluid is taken. I mean, a hot fluid is taken, and then it goes to the organic Rankine cycle, and then we generate power from there. Now, if you look at this simple figure, there are many things which a CFD engineer or a CFD enthusiast can contribute to, because we are talking about radiation, we are talking about conduction, we are talking about convection amongst these layers, and we are also talking about different phases. Phases also are available, which is at a bigger uh, level, at the plant level. So again, here, if you see the schematic, we are talking about again the turbine, which NAL had the core competence. However, extending that for the solar pond, the entire architecture was conceptualized and it was realized along with Pondicherry Government College and the local governing authorities of Pondicherry. Now, again, here, if you see, there is lot of thing that the CFD community, open foam community, can contribute to. So, like we are talking about turbo machines like the turbine or the pumps over here, the hot water pump or the organic compound circulation pump. We are talking about the heat exchangers over here in the form of vaporizer. We are talking about the condenser, which is nothing but the heat exchangers. We are talking about the cooling towers. We are talking about the solar pond itself. We are talking about sun and the radiation. So this itself starts posting lot of issues and lot of questions to the community, this August audience, uh, about how they can help in designing a better system. So we have some baseline systems. So given that, using the know-how in CFD, how do we improve the performance, or how do we understand the working, the operation of that? How do we forecast the power generation? All these things, probably this is the forum which can answer these kind of challenging questions. So again, as we mentioned, this was again a collaborative work with Pondicherry government. The funding was from the Planning Commission through the Pondicherry government, and the electrical department, Pondicherry government, and the Pondicherry Engineering College was involved. This is the view of the solar pond, which was realized at Pondicherry. And I mean, there were three ponds mentioned in the previous slide. So this is the other one. And as you would have seen in the previous slide of harvesting geothermal energy, the system remains the same. So we are talking about the piping systems, we are talking about the heat exchangers, we are talking about the generators, we're talking about the turbines. There is the disassembled view of the turbine, the actual turbine which was used for generating power. So the architecture remains the same. It is the source with which we tried playing and then exploring the possibilities of harvesting the renewable energy in those forms. So in the previous attempt, it was the geothermal wells which were giving us the thermal energy, which was later on converted into electricity. Whereas in this case, an artificial way of generating the thermal reservoir in the form of a solar pond was used as a reservoir for the thermal energy. Now, having said this, let us now have a quick glimpse of the wind energy harvesting efforts. Now, the question may be there that we are talking about turbo machines, so how does this fall under that category? So, the wind turbine is basically an extended turbo machine. The fundamental definition of a wind turbine is it's a turbo machine and it's an extended turbo machine where you, unlike a conventional turbo machine where you have casings and enclosures. Here it is open to the atmosphere. So that is the reason why it is the extended form of a turbo machine. But the fundamental theories remains same. The fundamental physics of a turbo machine remains the same. So, even though NAL is predominantly known for the aerospace flavors and aerospace products and technologies, wind energy had been researched in NAL since its inception in 1959. So, this gives you a chronology of various activities at NAL related to wind energy harvesting from 1959 till the present time. So we'll have some picturesque view of these things. So we started by understanding what exactly were the wind turbines that were imported, and at the same time we had some in-house designs also during 1959, 60s, and that period. So as you see, those systems were all put in the same wind farm, and they were tested to understand the nuances of the operation of these systems. You can see over here various other models. You can see here one more. And while these in-house designs were developed, there was also need to test them, the structural integrity. So this is again a glimpse of how in those days we tried to establish the structural integrity. Of course, it may look very funny today, especially when you are all aware about the sophisticated DAC, data acquisition systems, and strain gauges, and many higher level measurement schemes, experimental approaches to assess the structural integrity of any component. We have filtering arrangements and back kind of things. It may look very funny that people themselves, and of course let me mention here those who are standing over here, some of them are the technical officers and some of them are also junior scientists that were trying to ascertain the structural integrity of wind turbine. So while it may look very funny, if you see it from the dimension of time, this was the same time when ISRO used to transport rockets on bicycles and satellites on bullock carts. So I mean, there's nothing wrong when we first see the previous picture and laugh on that. But the fact is, like, today we have moved along. Today there is no need of telling where ISRO stands. But even ISRO during those initial days when there were a lot of technology denials to India, they had to have their own ways, and it was a very tough way, as you can see over here. So, not just the horizontal axis wind turbine, NAL also tried to understand the performance or the design aspects of uh, the lift type vertical axis wind turbine. You see a Darius wind turbine, or the drag type of vertical axis wind turbine, a Savonius rotor. You can see over here, and even various architectures of the lift type vertical axis wind turbine with straight blades. We call them gyro mills, and not just made the metals or composites, but also from fabric. So here you can see an example of a sail type horizontal axis wind turbine prototype that was installed at NL during 1970s and 80s during that decade to understand the operation and the design aspects of wind turbine. And even during those days when uh, wind tunnel testing was a very privileged facility to have, NAL tried to understand the performances of wind turbines by doing the wind tunnel testing during those times. I'm talking about 70s and 80s, the decades in 70s and 80s at IISC, even our in-house wind tunnels in NAL, we tried to understand the finer details of the designs using these wind tunnel testings. Now, one aspect of harvesting wind energy is to understand the performance, correlate that with the design, and then try to do it. But the main thing is what is the driving force. So one needs to know what is the wind potential that is available in a particular area. So in that context, NAL built the first wind map of India, as you can see over here. And this fact has been also acknowledged by National Institute of Wind Energy in their Wind Atlas map. They have recorded this fact that it was NAL which realized the first wind map, of course, with the help of IMD and other line ministries. But this was the thing that NAL did during the 70s and 80s, where when things were still germinating in India in terms of wind energy harvesting. Also, we experimented with various configuration, and one of the approaches is to anthropogenically generate the wind by mounting a prototype over a van, and all the instruments are housed inside the van, and then the van is run at a predefined vehicle speed so as to artificially generate the wind. This is an interim way of testing wind turbine between a wind tunnel and the actual field trials. The issue with the wind tunnel, as we all know, will be the various factors. The scaling issues will be there, and then you have the blockage issues because of the confinement. Whereas in the case of field testing, you may have to wait for certain winds conditions to naturally occur. So that may occur today, or that may occur after 6 months. So then it is very time consuming. So this approach of tau testing is an interim approach wherein you can artificially generate the wind by driving the vehicle at a certain speed and then acquiring the parameters like what is the electricity generated from the rotor, if there are any vibrations, what are the vibration levels. All those things can be recorded. So this is a glimpse of the tau testing and the field trials of one of the systems that was developed at NAL. And we also did the digitization of the geographic features which were proposed to be the sites for setting up the wind farms, because it's important to understand the difficulties in reaching those areas. One part is, yes, you say that there is a potential of the wind energy to be tapped in this location, but then unless we know the local difficulty to reach those areas, it may not be possible or useful. The information of wind may not be useful. So in that context, NAL also did some digitization of these kind of local geographic features, which helped in taking decisions on setting up the wind farms. Of course, it was not just that NAL did the work in India, but if you are aware, every year there are these Antarctica missions that is launched, and different countries come together and then they go to Antarctica and they do research on various aspects which influence our life. So in that context also, in during few of those expeditions, NAL went and it participated in those expeditions, and some wind resource assessment was done in the Indian Antarctica Research Station, Maitri. Of course, today we have two research station, Maitri as well as Bharati. But during those days, I'm talking about 95 to 2002, we were having only one research station, Maitri. So a glimpse of our team, NAL team, was standing here, and the met mask which was installed there, and some wind turbines that were also installed over there for doing the energy harvesting at Antarctica in our near to our Antarctica research station, Maitri. And apart from that, while this was going on in Antarctica, NAN also took up some activity on power curve measurements. Because having known how do you design the wind turbines, having known what is the wind potential, and having the experience of doing the entire prototype manufacturing, installing, and then doing the trial, the final thing is how much energy the cluster is producing. So in that context, NAL also did the performance studies of various wind farms during those times when this sort of skill set was not available. Of course, today, if you ask NRCon, Suzlon, or GE, their teams do have their in-house expertise in this area of power curve measurements. But I'm talking about those days when it was still in nascency in India. So NL was the only agency, but then now today you will find lot of people who have these capabilities. And then during the time when I joined NAL, it was working on the grid connected system. So here you see a glimpse of a 300 kilowatt wind turbine that was majorly to help one of the local textile industries in Coimbatore district. And we also had worked on the 500 kilowatt development of a 500 kilowatt grid connected wind turbine. This was also a prototype, a full scale prototype that was fully designed, then fabricated and installed, commissioned, and field trials were also carried out in the Coimbatore region. It was Kethanur. We had a collaborator, Sangeet, Sangeet group of companies who had collaborated with us. So, along with them and our sister labs, SCRC, we had carried out this particular prototype development and demonstration. Now, after the grid connected systems, we also ventured into hybridizing the wind turbines with the solar PV panels because wind is notorious for its intermittency. And if we are talking about a sustainable solution, the COP30 is presently going on at Brazil, and we are expecting to have a lot of recommendations from COP30 conference on the sustainability and how to reduce the carbon footprints, reduce the ill effects of greenhouse gases. So we need a sustainable solution, sustainable renewable energy solution, which unfortunately cannot be provided by either wind or solar in isolation. So that was a thought process with which we embarked on hybridizing our wind turbines with the conventional solar panels, and we had three prototype models that we generated out of this work. So the first one was a 1 kilowatt system, which is given as a technology infrastructure to the educational institute. Here you can see some of these installation across Bangalore as well as across India and even in our sister labs, SCRC and CBRI. And then the second prototype, that is the 7.5 and 7.5 kilowatt wind solar hybrid system, was targeted for agri pump application in a standalone manner. And the third class was the 10 kilowatt by 10 kilowatt wind solar hybrid system, which was targeted at catering to the energy needs at a community level in a rural hamlet where weak grids exist or the grids are, the availability of the grid is not so frequent. We have often the power cut over there. So this architecture also has the option of absorbing any other form of energy, and we had an integrated controller come inverter which could work in both islanding as well as anti-islanding mode of operation. Eventually, what a lab like NAL does is once we demonstrate the prototype, we ourselves don't take up the production or the marketing or commercialization. We tie up with the MSMEs or with any companies who show interest in taking our technologies to the market. So, in that context, the systems that were developed, the hybrid systems, they were transferred. The technology was transferred to local MSME in Hyderabad, Mrs. Green Energy Private Limited, a Hyderabad-based firm. These are the glimpse of that. So the technology transfer document. And as I was mentioning during the initial slides, that we do have international collaboration. So while the previous slides were more on to the product development, here it was more on the research flare of renewable energy harvesting, the wind energy especially. And the focus here was on the rain erosion coating developments. So this was a work which NL did along with two MSMEs, one in Pune and one in Chennai. And then along with the consortium also had NIWE, National Institute of Wind Energy, which is the nodal agency for wind energy in India. And IIT Delhi, Professor Puneet Mahajan, he was involved in this noble venture of looking into developing the rain erosion coatings for the wind turbines. What happens is an offshoot of that, something innovative comes out. So this particular patent came out as one of the IP outputs of our venture into the wind energy uh, uh, domain. And now, having said all these, picturesque stories, let us have a look at some of the areas in wind energy harvesting where we try to apply the capabilities of computational fluid dynamics to have more efficient system. Now, this is a nice comic from NREL, which says that if you leave the design of a particular system, so in this case it is the wind turbine. So if you leave these designs to the respective disciplines, how would they physically look? So, if you have an aerodynamics looking at the turbine design, you'll have aerodynamically efficient blades which are very, very thin. And then similar things happen if the control guys look into that and design, or the acoustic guys look, or the electrical engineers, if they look the architecture, or if it's a manufacturing or structure, or the weight and mass CG guys, or the service guys, if they look into the design, this is what can happen. So primarily, what we are saying is, since the final product has to optimally work, all the multiple disciplines have to come together and work in synergy. So in that context, the first thing that came out was like this was a joint work with a student Shubham Deshmukh from MNNIT Allahabad Prayagraj. He came to NL for his internship, and then he did this work on the question that we posted to him, like, if I aerodynamically shape a blade, it will have a very non-linear chord distribution. However, it may be difficult to manufacture such a complicated shape. So, in the benefit of or the ease of manufacturing, if we can linearize the chord distribution, will there be any effect on the performance? So this was the problem statement that was posted to Shubham, and with the use of CFD, he tried to answer that question. So here you can see that this is the shape of a excellent aerodynamically efficient blade, whereas this is something which the manufacturer would like to see. So when you make these two blades, how will the performance look? So he underwent all these conventional steps in CFD, like making the geometry, and then making the grade, and giving the boundary conditions, running the simulations, and then post processing the results, and then finally telling us that even if we linearize the chord, uh, it is going to produce less power as compared to what would have produced if it was a highly aerodynamically efficient blade, but the losses are not very significant. But as compared to that, if I have to make an aerodynamically efficient blade, the cost that may be involved in making that may be very high. In which case, there may be issues in its commercialization at later stage. So then we may go with a simple linear chord distribution, which may not be so efficient as the non-linear chord distribution based blade, but it will serve the purpose. So this was how he helped us to go ahead with some practical decisions that had to be taken. Of course, another thing that he tried to do was understand the acoustics of the blade, given if you change the tip. So, in fact, this work was then translated into the 5 or 7.5 kilowatt wind turbine blade design, which was for the off-grid agriculture application. So here again, he underwent the same rigorous process of CFD, of meshing the blades and then doing the simulation for different pairs of wind speeds and RPM. Basically, these turbines are variable RPM systems, so we don't consider the RPM to be constant. So each wind speed has a unique RPM at which the system will become stable. So at different RPMs for a rectangular tip and then for a SWOT kind of a tip, how were the fluid dynamics affecting the acoustics? So this is what he studied during his internship period. And I'm also happy to say that after he did his internship, he also came to IIT Bombay. I think Professor Sinha of aerospace. With him, he later on worked on single and two jet subsonic jet flows. Presently, he is abroad doing his doctoral studies. The next joint work in this direction, which I had presented during my first presentation, it was almost 1 year back, was with another student from Manipal Institute of Technology in Manipal. This was on understanding the standstill characteristics of the bio-inspired vertical axis wind turbine rotor. So again, here OpenFOAM was used for the simulations, unlike the previous case where ANSYS was used. The third work was with a student from Diet, Pune, and he worked on the bionic ram air turbines investigation. So basically, the ram air turbine is an auxiliary power supply unit. In fact, when the unfortunate incident in Ahmedabad happened in June month, this was one of the aspects that was captured in the video, the ram air turbine, which had popped up just before the aircraft crashed. So that was an indication that both the power plants had failed. So unfortunately, I mean, the inferences from the CCTV camera footage, which showed the ram air turbine had deployed, only indicated that the supply, the fuel supply of the aircraft, I think it was Boeing 7878, that had totally cut off, and that's why this ram air turbine it popped out. It was a very tragic incident in the history of Indian aviation sector. However, ram air turbine has a history of saving lives. For example, in 1983, the Air Canada Flight 143, which was cruising at altitude of 41,000 feet above ground, it faced a total energy flameout. And at that time, this ram air turbine it got deployed and it helped the fly-by-wire flight controls of that aircraft to gradually glide and then land safely. So 69 passengers were there and all of them could safely land. A similar incident happened in 2001 when Air Transit flight number 236 that also faced a similar both engine failure condition. And in this case, around 300 plus people were on board. But fortunately, because of the ram air turbine, the pilots could safely glide the aircraft and land it. And another example of ram air turbine saving the lives of the people is what is famously known as Miracle on the Hudson River. I think that there was a movie called Sully, which was based on this particular incident, wherein in 2009, a US Airways flight 1549, which was carrying 155 passengers, it experienced a bird hit. And both the engines failed, and then the rat somehow it deployed, and with the skills of the pilots, the plane could be landed not on land but on the Hudson River. So for those of you who are interested in this kind of failure things, you can see the movie Sully, which will be very much helpful, and it will also tell you how simulations help in understanding certain reasons behind the accidents. So now coming back to our main thing that we have already now seen what is RAM turbine and how it is important. So under this study, what we tried to do is, apart from the conventional wind turbine blade design approach, if we borrow the designs from the nature, whether what happens to the performance. So that was the focus of this study. So here you can see the unsteady aerodynamics that happens when a maple seed descends and it falls and it is rotating also at the same time. A little bit of a theory behind that, how exactly it happens. And we also are very much coming across the dragonfly's flight. So while the naked eye doesn't see the aerodynamics, when you do a CFD simulation, you see a totally different and a very exciting picture, which is seen over here. How the vortex patterns are getting generated, how they are propagating, how they are interacting with the wing. And since this is a tandem wing, we will have another uh, way of interaction. So the student, he tried to implement all these shapes in the open source code QBlade, and try to understand what will happen if we, instead of conventional wind turbine, if it is blade is made which is inspired from, say, the dragonfly's wing, or a blade which is inspired from a maple seed's wing. So how would the aerodynamics look? So this was something which is related to that. Of course, my affiliation with ACSIR helped us to also understand these things from experimental point of view. So basically, as we said, that we tried to take inspiration from the nature, and then we tried to mimic them in the engineering form by printing the shape using the latest 3D printing technologies, and then also checking whether we have got the things right or not by just holding the rotors with say two refills and just blowing some air manually, or doing a proper lab level controlled experiment here over here with proper data acquisitions, and trying to understand what the aerodynamics of this. So this was something which we did experimentally. After the end of my presentation, you will be seeing some more insight into how the FOSSEE family did the CFD part of this assessment. So that will be really interesting. I urge all of you to try to attend to that. And now we then come to the the challenges that the energy community is facing, and what is it that we are expecting. Already, while we were discussing and while we were looking at the geothermal energy based plants, or the solar pond based energy harvesting approaches, or in the wind turbine, we have been discussing this, so we can gradually increase our pace, because already we were a little late in starting. So if you see the various regions in India where the geothermal potentials are existing, whether it's Himalaya, North or Andaman Nicobar, Western Ghats, Godavari Basin, there are a lot of applications that are possible. Now, issues with this, primarily, one thing is the institutional challenges, which is like there are limited R&D centers in India when it comes to geothermal. A very handful of them, you can even count them at your fingertips, so really low. So that is one thing which is holding the innovations to get into the thing. Of course, these are more related to the government, like the policy and regulations, or the financial things, technological challenge. Again, when you say technological challenge, it's more about the engineering challenges rather than getting into the finer details of the system or the subsystem level. Of course, the awareness and the environmental challenges are also existing. Now, for the policy regulation, something has already been done. It is as recent as 15 September 2025, wherein the national policy for the geothermal energy has been released, and you can have a look at the detailed document. I would just like to bring to the information of the August audience over here, which is consisting of academia, that they are recommending to have center of excellencies in geothermal, And this is probably one area where a community like FOSSEE or the open form community can exorbitantly contribute. There's a good scope that a center of excellency is established probably in an academic institute. It could be IIT, it could be NIT, it could be a regional college, it could be a local engineering college on deliberating various design aspects, because this is the place where you can afford to deliberate on the detailed design. Of course, the engineering part and all will be taken care by the preceders and the successors of here. But then this particular thing is something which one can, keep in mind, because here is where the integration of science and technology is going to happen. So coming to that, what are the challenges? So as we have already seen, the organic Rankine cycle at its component level is consisting of the heat exchangers, then the turbines, pumps, the piping. So there were many talks in the past 3 days which touched upon the piping and also the thermal simulations. So probably those expertise can help us to answer the question, like, given an operating condition of the plant, what is the optimal design? Okay, so it is something like a inverse design where you are given the performance and then you have to design say heat exchanger or the turbine blade and also here there is a lot of expectations from the CFD community where you can extraordinarily uh, contributions can be made. The second part is at the system level where we are talking about understanding the optimal design or the operational parameter. So what this means is given a system architecture, what are the conditions under which it will perform at its best or at least at the optimal level. So again, this is more to do with the multidisciplinary simulations where you're talking about fluid flow, heat transfer, mass transfer, two-phase flows, vibration, acoustics. All these aspect is not unknown to the open form community. I mean, somewhere, even if you would have done a canonical study, you would have seen these simulations happening. Now it is the time whether you can, look it from an application point of view. The same thing happens here when we're talking about the system performance. So here the question is like, given a system, if it is operating at an ideal condition, what is going to be the output? And the digital twin is more related to given a system and given an operating condition, how would it behave? So a slight difference between these two, but again here, as you would see over here, and there is a lot of thing that the open form community can really help. And today we are talking about reduced order model. We are talking about machine learning models. So that also has an extraordinary, expectation from the CFD community because the data, the clean data based on which these models also will be created is very critical. And that is the responsibility of the CFD community or the open form community if we come forward to take this challenge. Now, coming to the solar energy harvesting, also since the working principle and the architecture of the overall system is similar, so you will find that many things will be matching. Like, for example, if it is a pond, then these are the areas where the CFD community can help us to ascertain the optimal geometry of the plant or the correct thickness of the various zones or the heat extraction system, whether it's properly optimized, the exchanges are working properly in the material selection also in some extent, especially the lining material, which will prevent the heat loss from the bottom of the pond. But if it comes to analysis or if it is coming to the performance evaluation, you will find that what we are seeing in the previous slides also, we are expecting similar things to happen. In fact, it would not be exaggeration if I say that each one row of these questions can be one internship problem for the interns of FOSSEE Open Form 4. Now coming to wind energy, again here NIVE has released a R&D vision document. uh, I'm just putting few things over here, especially to bring to the notice of the audience over here. The rotor design, which includes the aerofoil and wind turbine aerodynamics. So definitely, this is the area where the open form community can think of contributing to. Of course, offshore, onshore acoustics are there, which can be also looked upon. And again, here specifically in this document, in the long term goals, which is linking to SDG 7, SDG 9, SDG 12, and Sustainable Development Goal 13, they are specifically mentioning CFD. So it is explicitly mentioned in the vision document itself that there is a need for the CFD community to get involved in these noble efforts to harvest renewable energy. Okay. The only issue when you talk about renewable energy is the scale. So we are talking about a big scale, temporal scale, which can vary from days to weeks, or slightly lower scale, which varies from minutes to hour, or something which is varying within seconds. Now, depending upon this temporal thing, the modeling as approach will also change. Like when it's second, we are talking about the CFD based model. When it is minutes to hour, we are talking about the mesoscale modeling approach. And when we're talking about the weeks or days or months, it is the global circulation model, the GCM models. So again, here, how to network these various models to realistically simulate and realistically weave these temporal differences is another challenge that the CFD community needs to accept. And I think the audience here is very much capable of appreciating this, and also they will be very happy to, I think, accept the challenge. Of course, CFD in wind turbine helps at different levels, starting with the aerofoil. Then we have CFD happening at the blade level, and then at the rotor level, and then finally at the cluster level. So some glimpses like at the blade level testing, even a very trivial looking thing like the root, if it is properly shaped, you can get something like 3.5% higher annual energy production. So this is where CFD can really, help the community to come out with an efficient wind turbine blades. Of course, we have to see what sort of manufacturing processes have to be adopted to manufacture such efficient blades. Then, when it comes to rotor level, there are various approaches like the blade element momentum theory, the actuator disk, the actuator line, or the actuator surface, which have been adopted by the community. And these are also implemented in some way in the open form framework. The basic difference is the computational cost, which is associated with each of these approaches, and the approximation. So basically, the fan model is nothing but the actuator disk model, which is highly approximate, but the cost of computation is low. Virtual blade model is identical thing to the blade element and momentum theory. Again, here the approximation is a little higher, lesser compared to the actuator disk, but still there. And the computational times are also relatively more. We know about single reference frame and multiple reference frame models. We are very much aware of this. And the work what Shubham had done was based on the MRF models. The sliding mesh model is another approach where, for example, the vertical axis wind turbine simulation and the demonstration that you will see, this approach is only appropriate because it will not be suitable to use the MRF. Maybe the finer details will be explained by the CFD, the FOSSEE family member who will be presenting the case study, and then the dynamic mesh model, which is computationally very expensive, but approximation wise, it is relatively less than all the other models. And again, at cluster level, CFD can help understand the weight behind the rotors, or the physics which is underlying the cluster aerodynamics, and then trying to minimize these losses using the same CFD frameworks, and try to optimize the annual energy production. So it says that about 1 to 2% of the energy production can be improved if we properly cluster these wind turbines rather than just clustering them in a regular fashion. So here also, depending upon your focus, the resolution of blade, whether it is required. So, for example, if you are trying to understand the near wake dynamics, the blade geometry plays a role. Whereas if you are looking at the far wake behavior, it is not very much important to use the very detailed geometry. So here, if you approximate this as an actuator disk, you can still understand what is happening at the far wake, but not near to the turbine rotor. So this is a glimpse of the features of the wake, how it generates, and then how it propagates, and how the turbulence is of different scales interact with each other. Of course, turbulence is something which even the geniuses like Heisenberg or Richard Feynman or even Professor Lamb could not explain. So they could only give certain catch statements which are captured over here. And of course, we know about the turbulence models which can be used to capture this Reynolds stress, the two equations models, one equation model. So as we go forward to this, we probably the computational cost increase. Deliberately, DNS is not shown here, but of course, with the advent of neuromorphic computing or quantum computing, I think the audience can even dare to introduce DNS. I hope there may be some two views, but yes, I think we should try to see whether we can introduce DNS also over here. Of course, it's at this stage with the existing computational technologies, it may look a fairy tale, but may not be in say next 5 years. Of course, finally everything culminates into kind of a virtual wind turbine, wherein you have the rotor level studies happening with the wake and all those things. But of course, if you want to push the complications to a higher level, we can consider the multidisciplinary simulation problem, wherein we are talking about the offshore wind turbine, which apart from the basic wind turbine aerodynamics, will also have to handle the heaving, surging, and the swaying movements which are observed in the offshore locations, especially the floating offshore wind turbines. And then going forward, this is the wish list. Like, you can finally create a digital twin of the entire wind farm. If it is onshore, then we only need to worry about the atmospheric boundary layer. But if it is offshore, we need to couple atmospheric boundary layer along with the marine boundary layer, which will again have its own challenges. Of course, the levels of complications and the level of geometric detailings are different at these levels, but ultimately this will be something which will be really helpful to the industry. So this community, and as a longer goal or as a longer problem definition, should definitely keep the digital twin of a wind farm, and to extend the complications more, the digital twin of an offshore floating wind farm. I think that will be the ultimate challenge with this community. I'm sure with all the enthusiastic students and the professors over here will definitely agree to accept. So with that, I would just like to conclude that a lot of things are happening in the renewable energy sector, and academia and MSMEs are going to be very playing very important role in this noble venture of harvesting renewable energy. Of course, the innovative interventions from CFD community is imperative, and lot of contributions can be done from one form consortium, which we are today, having this event for. So, just like to end with a slok that from different yugas, the success is because of various aspects. So, when it comes to Kali Yuga, this is the present Yuga, it is only the Sang Shakti that helps us to move forward. So, then Sang Shakti is the form of consortium. So, we again, this is again, I have borrowed from my previous slide 1 year back, where the Nabla sign of open foam itself indicates that there is a need for academia and the industry and research organization like ours to come together, connect, and then try to contribute to the noble cause which will impact a common man like me to solve my day-to-day problem. So with this, let me acknowledge everybody who has been involved in making this event a grand success. Professor Bose from University of Birmingham, the FOSSEE family, IIT Bombay, our CSIR family members, and last but not the least, the audience who have taken their time and they are listening to my, pleas to them to help us out from this thing. And you can reach me on my emails as well as my WhatsApp credential for any queries. But rather than reaching me with a question, it is the other way round. I am actually asking for all of your help in meeting the challenges that we have seen in the past 1 hour with respect to harvesting renewable energy. So with this, I thank and I hand over the proceedings to the organizers. Thank you.
Thank you so much, Dr. Ray. It was I am not from the CFD background. Even I found your presentation very much interesting. It started with a story and ended with a sloka and so many of history, and then you are combining it with the present day, the modern technologies and all. So it was amazing. Uh, so thanks a lot. So any questions from the audience to Dr. Day now?
On a humorous note, it is like, if there are no questions, there are two interpretations. That either everybody has understood everything,
Yes.
or nothing has been understood. So I take it on that positive note that everyone has understood. Of course, I try to make the presentation such that somebody who is just starting also will be able to appreciate. I mean, there are no scary equations or no integration differentiation. It's all something which a common man comes across during his day-to-day life.
Yes, yes,
So
yes. Yes, and for the students, I will mention that there is a scope of doing internship under the guidance of Dr. Day through the FOSSEE internships and fellowships. So thanks a lot once again, Dr. Day.
thank you, ma'am.